Hello, my name is Andrew Geary and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. In this episode, I speak with Steve Sloan, Special Section Coordinator for October's The Leading Edge. October's TLE focuses on using geophysics to assess infrastructure, the roads, bridges, dams, railroads, tunnels that make our life easier around the world. Steve and I discuss how geophysics can be used to assess and monitor our roads and bridges, geophysics' role in planning and preserving infrastructure, as well as highlighting the 4 articles in this issue. Steve Sloan is a research geophysicist at the U.S. Army Engineer Research and Development Center in the Geotechnical and Structures Laboratory located in Vicksburg, Mississippi. He specializes in near-surface seismology, including high-resolution shallow seismic reflection, refraction tomography, and surface wave methods. He currently serves as the past chair of the SEG Near-Surface Geophysics Technical Section and is a member of the SEG Council and the editorial board of The Leading Edge. Now for our conversation. Okay, so I'm going to start with a simple clarifying definition of what is infrastructure.
I'd say it's the basic physical structure and facilities that you need to operate, whether that's on a local level, a national level, or an international level. So think highways, bridges, airports, railroads, pipelines, levees, things that are related to your everyday tasks, driving to work or getting water out of the tap or electricity in your home.
I hadn't thought about the water and the tap being infrastructure, but that definitely makes sense. Why are near-surface geophysical methods especially suited to access and monitor infrastructure?
Well, one of the advantages of geophysical methods is that they can provide continuous sampling of cross-section or an area, as opposed to discrete point measurements that can be very localized. So geophysics can't really replace those types of measurements, especially that a lot of them that are used in the engineering community, mostly because of a lack of resolution or some of the quantitative uncertainty. But because you can acquire them over larger areas, you could use those to identify anomalous areas or potentially problematic areas that might require additional sampling with those conventional methods.
How would using the tools and techniques of near surface support decision makers in charge of improving the infrastructure, these roads and bridges and other things?
Well, I think there's several different ways that geophysical methods could be potentially used. Some of those might be on demand. So if you had, say, a major weather event, hurricane or flooding or something like that, using methods to go out and survey roads or bridges to identify problem spots that may not be immediately evident from the surface, or looking long-term, looking at multiple surveys over time to see how structure changes over time, or maybe to detect a sinkhole before it reaches the surface, or look at increases in stress in a bridge pillar due to bridge scour. Could be embedded sensors, putting fiber optics in roads or levees during construction, using a method like distributed acoustic sensing to monitor strain over time. I think in general, in short term, it could aid in prioritizing areas of emphasis, and in the long term, identifying those areas of interest before they become immediate problems. So kind of being proactive instead of reactive.
So we are both based in the United States, but this special section in the Leading Edge on infrastructure looked outside of the United States as well. Could you briefly explain how geophysics was used by Yilmaz et al. In planning for a subsea tunnel in Turkey?
Sure. The municipal government there in Istanbul is planning to construct a second subsea tunnel. There's lots of work that goes into the pre-construction planning phase, identifying potential sites, collecting the property information, looking at identifying the potential risks so you can mitigate those. And the authors used high-resolution seismic surveys to go through and map the soil-bedrock interface and build a geologic model of the project area, which then could be used to help plan geotechnical boring locations and the depths that those needed to go.
Hayashi et al. Discuss non-invasive methods for levee inspection that they developed and carried out in New Orleans, Louisiana. How are these methods an improvement over the conventional levee assessments?
Well, one thing I want to stress is a lot of these aren't necessarily meant to be a replacement. One of the advantages here with what the authors were doing is one, it's non-invasive, so it's surface-based measurements. You don't actually have to penetrate the levees. Another is the speed of acquisition, so they can collect a lot of data relatively quickly and cover a pretty large area. So it's not going to replace those really high resolution engineering measurements or tests that they're using, but they can gauge kind of the status of a larger area much more quickly than the invasive measurements.
Park and the co-authors discuss a particular method that provides a level of quality control to road construction. How does this near-surface application improve upon the traditional approaches to evaluate roads?
So some of the more conventional methods, such as penetration tests, they're point measurements. So they take them every so often and use that information for their testing and their modeling to make sure that they're meeting the specifications. This one's kind of the same boat. So the surface wave methods that Park's describing won't replace those, but it can augment those by being able to cover a larger area. So instead of discrete point measurements, you're getting kind of a cross section of the area at large, so you can see how those properties change over the project area.
When you look ahead, what role do you see near surface geophysics playing in the planning and preserving of infrastructure?
That's an interesting question. I think technology has really grown in leaps and bounds, even in my relatively short career so far. So I think a lot of that remains to be seen. There's new methods coming out, new processing techniques as our computing power gets stronger. There's a lot of things that we can do today that we weren't even thinking of a decade ago or 20 years ago. So it'll be interesting to see how technology really opens up some different avenues for whether it's embedding sensors or doing real time or near real time monitoring in the future.
Is there a particular challenge within the near surface work that you do? Is there something you're particularly hoping technology can address in the near term?
I wouldn't say there's anything particular that I'm hoping to address. The one of the big challenges that you face on the near surface side is just the economics of it. So unlike, say, the exploration industry where it's profit driven and there's an underlying reason to go out and collect geophysical data, and ultimately that's to help you find reservoirs and get the resources out. On the engineering and environmental side, it's the opposite. A lot of times they're not, at least not on the face of it, delivering something to the bottom line. So it ends up costing money, but they don't necessarily see the direct translation to cost saving. So I think that's one of the challenges that really needs to be addressed. And how do you show that on the bottom line going into the future?
For the non-near surface geophysicist, what could she learn from reading these articles in the special section?
I think it's mainly it's different applications of the same types of physics that we see for the exploration side. It's just at different scales, and there's different challenges associated with it. So there's lots of different ways that geophysics are being used around the world for a whole lot of variety of applications, and this highlights just a handful of them.
This kind of echoes your previous answer here. One of the common themes I found in these papers is that near surface is a cost-efficient method for many public projects. So how could geophysicists working in this area advocate for these methods to public officials and other decision makers?
I think the big one is showing a direct cost savings. And safety is a big driver on the infrastructure side, but it has to be done with some reasonable cost efficiency, right? So we can go out and survey thousands of miles of levees, but that's really expensive. So coming up with new and innovative ways to do that in a cost-effective manner, but being able to show that. So a lot of this is the salesman piece, right? As geophysicists or scientists or engineers, a lot of times we're not necessarily the best at communicating things at the technical level to people that make those decisions. So the communications piece, I think, is going to be a big one.
What was one thing that surprised you in these papers?
For me, it was the diversity of applications out there that were covered in just a handful of papers. We got covered water, land, body waves, surface waves, active seismic, passive seismic, tunnels, levees, and highways. And that's just with seismic. That didn't even include GPR or magnetics, gravity, or a lot of the other near surface methods out there.
What do you hope readers of this special section take away?
That there's a lot of work going on out there, and a lot of innovative work that we don't see a lot of, but it's got the potential to affect our everyday lives. So even though we don't see it, and even though a lot of the stuff we take for granted, the conditions of roads and bridges and levees and waterways and things like that, is still an important piece that we need to think about. And there's folks that are out there that are thinking about it and trying to come up with innovative applications for it.
What kind of applications or learnings did you yourself take away from these articles?
I would go back to the diversity. So myself, I work in near surface seismic methods, but even I was surprised kind of looking at the submissions at just how much different stuff was going on out there that I'm not necessarily keeping track of. So there really is a lot of interesting work out there, and this just scratches the surface of it with just a few papers.
What should I have asked you that I did not?
One thing about all this is that it's I don't want anybody to think this is brand new and it hasn't been around. There's folks that have been working on highways and levees and things like that for a while. So and people working on the background to help cross that divide between geophysicists and engineers and policymakers. So it's really just kind of trying to bring that to the forefront and get folks out there to read about it and see what all is going on with it.
At seg.org/podcast, you will find the show notes and links to the October TLE issue. Subscribers can read the full articles online, and abstracts are always free. Follow Seismic Sound Off at seg.org/podcast to hear new episodes or subscribe for free on your phone. Seismic Sound Off is sponsored by the SEG Wiki, the place to find hundreds of biographies of geoscientists, open access tutorials, and ongoing translations of SEG's best-selling book, Robert Sharris Encyclopedic Dictionary. Type wiki.seg.org into your browser to visit the world's first online geophysics encyclopedia. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary. Special thanks to the SEG podcast team, Jennifer Crockett, Allie McGinnis, Teresa Reichardt, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.